All right, let's hit the ground running. Last class, we had some technical difficulties. I've since got the tech team in. Hopefully we have these problems solved, and it'll be a couple of clean classes in a row.
To work with. He's over here like, whoops, sorry.
Oh, yep. I do believe we have the problem solved. Today's program with the Earth Science guys went rather well. So I think we are going to have a clean program. It was with my computer. They needed the faster Wi-Fi because when I was moving the switch between documents, for some reason I was on the student Wi-Fi versus the Ethernet. I don't know, but the tech team came in, they updated Zoom, did all the work for me. So hopefully we're in good shape. So we did leave off in the middle of a lecture last time. But before we hop into the lecture, let's talk about tonight's work. First thing is our current events. You see here where we ask for articles within the last 2 years. I'm going to expand that until the last 10 years. I'm doing that for a couple of reasons. The first reason is when I ran some Google searches on exploring the seafloor for natural resources, what is a natural resource, resources from the ocean, and then looking at things like petroleum, food resources, sediments, different resources, mining the ocean. There's all different ways to attack this. I came up with a fair amount of articles, but I think we're going to get a lot of repeats with a class of 30 and a restriction of 2 years. It become rather boring for me to read the same article review from 15 different students. The second reason was I had a student email me saying they're having a hard time finding articles within the past 2 years. I don't know if they were searching the same parameters I was or what, but I thought it might be easier for you, the student, to find articles if you had a wider time frame. I also found some articles that were interesting that were maybe 5 years old that I was hoping, or somebody is not muted, so if that, you could just make sure that you're muted, that'd be great. But I thought some of these articles were too good to exclude. So I am expanding the search parameter back 10 years. I haven't gone through every single module assignment yet and changed the 10 years, but I did email you all, and I'll just make the announcement that, from this point forward, the last 10 years will be considered fine for your current events. And then, as I was doing these Google searches and I seen, the APA literature, I thought to myself, when I was in college, I don't want to date myself and look like I just hopped off my dinosaur to teach you guys, but all of our research was done with those pull-out Dewey Decimal System cards, and then Xeroxing the book with a copy machine. Copies cost a nickel, and then you push the button, you get your copy, and then you sit down and handwrite everything, and then pay someone who's good at typing to type your projects for you. $1 a page is what it costs. And boy, you guys have it different. So when people ask me how to best research, sometimes I am not an effective helper because I'm not as modern with my research as you guys might be. So I went to the student center today and I asked, how can I give information to my students that's a little more current than maybe I would know? And they directed me to this website here, the Learning Resources website. And you can see they have a live chat for Ask a Librarian, emails or texts. Also, when you click on the research guide, you have your how to do an APA correctly. You know, I mean, we're not really looking to find the most difficult articles in databases. We really are hoping to find articles that everybody would read, you know, so I don't mind Google searches versus database searches. But it's handy to know where all these databases are in case you're in a class where you have to do formal research. And they have them all located right here through the different pages. So I wanted to bring this to your attention because it's very handy, and we didn't have these resources back in the 90s when I was getting my graduate degrees, or the 80s when I was getting my undergraduate degrees. We just didn't have these resources. So I wanted to point them out to you. Now this week, you know, tonight you have a quiz and your article reviews. Next week, you only have one assignment due on Wednesday, and I flipped it to the discussion. Before it was graphing the ocean floor, or graphing the ocean. I apologize. The ocean's layered. We're going to cover that next week. So I kind of put the assignments out of order. And as I was going through my lesson plans for this week, I noticed that the discussion that was originally listed for next week's work fit perfect with what we were talking about, the natural resources in the ocean, because it's mining minerals from seawater. And then the graphing the ocean, which was originally scheduled for this week, went perfect with what we were doing next week. So just for an announcement, and I have it up on the screen now, I went through the syllabus and the due dates, and I switched the graphing ocean data and the discussion forum. So next Wednesday, you have discussion forum 3 due, not graphing the oceans. And that change has been updated in the syllabus schedule as well. And I wanted to make sure, because sometimes people print things and put them in their calendars, and I didn't want anyone to open up the graphing the ocean data before we had a chance to cover it and go, oh my goodness, I have no idea how to do this. So next week we have discussion forum 3 due. The following week, which is way in the future, we're going to have graphing ocean data. It's based on the 3 layers of the ocean, which we will talk about next week. So this week we got our current events and our quiz. Next week, the only assignment that's due is a discussion forum. Okay? I wanted to make that clear. As I was going through everything today, I noticed I had them out of order, and I did not want anyone to get confused or hit the panic button because we did not cover the layers of the ocean yet. So that's it for the announcements and talking about the assignments and the work due. We will get back into the What is Water lecture that we were working on. Let's see if I can. Heavens to Betsy's. I have a, there we go. Okay, now I think we froze, if I'm not mistaken, on number 20, and I worked ahead a couple of slides before it was brought to my attention. So we will pop back to 18 because that's kind of where the story of these phase changes begin. Now, remember, we went through hydrogen bonding, why water is a liquid, and all of these unique properties that this hydrogen bonding lent to water. Now, water is the basis of all life. You know, living things can live without oxygen, and oxygen is probably the number 2 because multi-celled organisms need oxygen, because when you use oxygen to liberate energy, which is called respiration, you get a lot of energy when compared to anaerobic respiration, where you get energy. It's 2 ATPs for anaerobic respiration. What an ATP, which is adenosine triphosphate, that stores energy in a high energy bond. You break it, you give off energy. And anaerobic only produces 2. Aerobic produces 38 for a 36 net, because the first step in anaerobic respiration is an anaerobic respiration. So you get 38 ATP, 36 net ATP, which is far greater than the 2 you get for anaerobic respiration. So us complex living things, whales, crabs, utilize aerobic respiration, and that's why oxygen is so important. But living things can survive without oxygen, most of them single-celled. Water, though, is mandatory for all living things. So water exists in 3 states and moves state to state. And we call, when it moves, a phase change. So when you add heat, you get positive phase changes. When you lose heat, you get negative phase changes. And anything that basically melts, you know, organics, when you heat up, sometimes burn, but anything that melts, you wind up with a heating curve. And here's water's heating curve. It's 3 states: vapor, water, liquid, and ice. When you reach the melting point, you undergo a phase change. If you're gaining heat, it melts. If you're losing, if you're gaining heat, it melts. Yeah, if you're losing heat, it freezes. We call that melting. Right there, melting, and then freezing. When you add more heat, you have your liquid water. Your phase change here, adding heat, is your boiling or vaporization, and then cooling is condensation. You can see the latent means hidden, because temperatures aren't changing when that heat is being exchanged at the phase change point. It's only 80 calories per gram to melt ice, or negative 80 to make ice. It's 540 to vaporize water, or negative 540 to condense water. Negative 540 condense water, 540 to vaporize water. Think about when you get out of a swimming pool and there's a little breeze, you catch a chill, even if it's 90 out. You know, you dry off. And why does your body perspire? To get rid of heat. See, 540 calories is lost per gram as that occurs. So your body sweats so that water can evaporate, and it pulls heat away from you. When you get a chill getting out of the pool, it's pulling that heat from your body. So water is very, very, it has a high heat of fusion. So, and a high vaporization, high heat capacity. When you jump into Crystal River, which I love to do, Crystal River and the natural springs are beautiful. I'm sure a lot of you have here. They run about 71 degrees Fahrenheit. You're cold, and you can't stay in too long. You know, over the years, I've developed a little better than most. So I used to run a lot of field work to the springs, and it was always my joy to watch students jump in and scream because it was really cold and they weren't expecting it. And I guess I got a sick sense of humor, but I kind of chuckled because I was in there for a long time, but I got used to it. It's cold. Water pulls the heat from you. 72 out is not that cold in the air, because air has a different heat capacity. So water, you know, you lose heat and you go hypothermic very quickly in water. versus air. So this is the heating curve of water, and the latent heat during a phase change stays the same even though you're adding or subtracting heat. So the heat of fusion is the amount of energy it takes to melt or thaw. The heat of vaporization is the amount of energy it takes to condense or boil. And then we just got to this slide last class when I was told, hey, we're stuck on slide 20. So here is an example of what we call thermostatic effects, or water effect on climate. So this here tells a tale. Here's the United States. Our prevailing winds are called westerlies. And when we study climatology, we're going to learn about the westerlies, and they blow across the United States. So the weather and air comes off of the Pacific Ocean. It's very moisture laden. It's also cool because the California current's cool. We'll tie that in when we cover currents. So here in San Francisco, here's the heating curve. In the summer, you know, it's not very warm. You know, we're in the 60s. In the winter, lowest it'll get would be high 40s, but that's not super cold. Very moderate temperature. Always cool, very moderate. Because this air is coming off of the ocean, and water does not change temperature very readily. So it's a very consistent temperature. As the wind blows and our weather system moves across the United States, you know, granted, remember 0.2 was the heat capacity. So the air heats up greatly in the summer or cools off greatly in the winter. So by the time you get to Virginia, you have highs and lows, much greater temperature range. So a maritime climate is a climate that is moderated by water. They tend to have narrow temperature ranges, and depending on where they are, they can be warm or cool. You know, we have a very maritime climate here. We're right about here. We get our westerlies coming off the Gulf, but that Gulf is warm. So we are warm and humid for the bulk of the year. So our heating curve would be fairly similar to San Francisco's, except upside down and a little higher, you know, so we'd be a little higher. We have a maritime climate as well. So maritime climates tend to have a narrow temperature range. Continental climates, which the main influence comes from land, tend to have higher highs and lower lows and more extreme ranges. And that's called the thermostatic effect of water. So when you compare and contrast climates, you'll see that proximity to water, and not just proximity to water, but the currents and the temperature of that water have a great deal to do with your climate in an area. So the first thing we talked about, I believe it was last week, we mentioned how latitude plays a role in climate. And now we can see how proximity to water, and not just water, but the type of water, whether you have the warm waters of the Gulf or the cool waters of the Northern Pacific, how water factors in the temperature. Another property of water that we mentioned, but we need to look at, is why it expands when it freezes. Now, when I was a youngster, I threw a Coca-Cola in the freezer, wanting to get it cool off fast, and I forgot about it. And when I came out, the can was all bloated and the top popped off. And I was wondering, I wonder why that happened. Most substances, when you cool them off, they become more dense, take up less space, and sink. And that is true for water up to 4 degrees Celsius. 3.98 to be exact, but 4 degrees is a nice, easy number to remember. At 4 degrees, water tends to crystallize, and the crystal, notice, has air spaces in it. So up until 4 degrees, water condenses with coolness. After you cross that maximum density, you start to have the water line up and the density raises until you get ice, which is not that dense at all. And that's why ice floats, a lot of air spaces. So the hydrogen bonds form crystals and ice floats. So a property of water, a unique property is solid water is less dense than liquid water. And that's more the exception than the rule. Solid are usually more dense than liquids unless there's a lot of airspace. Well, think of a boat. The metals made in a boat are far more dense than water, yet a boat floats, and that's because it's cup shaped and full of air, and air is a lot less dense. So the air there, wood, wood floats because there's a lot of air in the wood, the less dense. Ice floats because there's a lot of air in ice when you compare it, so that makes it less dense. Now, evaporation only occurs at the surface, and you don't need to be above the boiling point for evaporation to occur. It's a molecule by molecule off the surface because water is so light. So that's all with water. So this image here kind of sums up that heating curve in a visual way. You have 100 calories to heat up liquid water. 540 calories causes that water to boil or condense. Negative 100 calories cools it off, and then negative 80 calories freezes it because the latent heat of fusion is 80 or 540. So let's kind of summarize up what we said. And interesting here, I talked about the sweat. When we start to drop down below the freezing point here in Florida, which occurs, but it doesn't occur that often, farmers turn on their sprinklers right before dusk to wet their plants, because if that water were to frost up, it would pull 80 calories off of the plants and keep the plants warmer. So ice acts like an insulator sometimes, and as something freezes, it would remove that take 80 calories to freeze it, and it would protect the fruit. So farmers, especially citrus farmers, if there's a freeze warning, turn on the sprinklers right before it gets dark out, so the ice can freeze, insulate the plants, and pull that negative heat as opposed to having their fruit freeze. Because, thermal expansion, think about that, because water expands, if water is to freeze in a cell, it can expand, and many times it would rupture the cell and it would kill. That's what a freezer burn would be on a steak, would be that outside of the steak, the ice crystals would broke those meat fibers, the proteins that make the muscle. So that's freezing, thawing, and the thermostatic effects of water. Now, the composition of seawater, because water's polar, salts, ionic substances dissolve in it. So things that are ionically bonded dissolve in water. So water is 35 parts per thousand solid, and then 965 parts per thousand water, or 3.5% dissolved solids. The most common dissolved solid is chloride, followed by sodium. So sodium chloride is the most common salt, but you also have sulfate, magnesium, calcium, potassium. You have a whole slew of micronutrients and ions, we call them electrolytes, dissolved in water. So seawater, these salts came from volcanic eruptions, chemical weathering of the rocks, especially early on, because if you recall back, ocean formation, outgassing from the volcanoes, and then weathering and erosion from the precipitation caused the saltiness of the oceans. Now, over time, our oceans have stabilized their salinity. So right now, we are in what we call constant proportion. Our seawater overall stays about 35 ppts. Of course, near a river mouth, salinity is less. In an evaporation basin, salinity is more. But most of the ocean is cold, dark, and 35 parts per thousand. The ocean composition is fairly stable now. The ocean is a solution for the most part, consistent throughout. A solvent is usually the liquid. It's what's doing the dissolving. Water is the solvent. We consider water the universal solvent because all polar molecules can dissolve in water, and ions dissolve in water to a degree. You know, some don't dissolve as well as others. This reminds me, when I was a kid, we used to buy oil paints. Oil paints were now they don't really sell them. They sell acrylic paints or water-based paints, but we got real oil paints on those paint by number kits. And we were young, we'd get it all over, and we'd go to wash our hands, and the oil wouldn't come off. So Pops would have to take us out, take a rag of gasoline, and clean us off with gasoline, because water is a polar solvent. Hydrocarbons and oils and other organics are not polar. So you need a non-polar solvent to dissolve non-polar things. So oil can dissolve in non-polar solvents, but not water. I'm happy Dad didn't smoke, or else I might not be here today after he washed me off with gasoline. But solutions. The solvent does the dissolving. The solute is what's being dissolved. It's a solid or a gas. It's usually less abundant. I say gas because gases are dissolved in ocean water as well, and they're so important. Fish intake oxygen for aerobic respiration. That oxygen is not part of the H2O water molecule. That oxygen is dissolved oxygen, similar to the oxygen that we breathe in from our atmosphere. It's dissolved O2. Algae intake carbon dioxide for photosynthesis. It's dissolved carbon dioxide, CO2. So oxygen and carbon dioxide are just two of the gases that are dissolved in water. Okay, so the solvents, you have polar or non-polar. We mentioned that. Water is considered the universal solvent because it is polar and other polar things dissolve in it. Now salts, because they're ionically bonded, they're made of your metal, which is a positive ion, your non-metal, which is negative, and then water dissolves them. The primary is sodium chloride, but as you saw from the list, there's many other dissolved ions in water. I'm not gonna say all of them because that's a blanket statement, but most of them can be salts when water evaporates. And that's how evaporites form. The amount that dissolve is called solubility. It depends on pressure, temperature, and the nature of what you're dissolving and what's being dissolved. So let's talk about water. Pressure. Gases dissolve better under high pressure. So I was a scuba diver for many, many years, and you go down and your big fear is coming up too fast. And the reason is when you're at depth, say 80 feet, you're sitting at, every 33 feet is an atmosphere. So at 80 feet, you're sitting at about 2.5 atmospheres of pressure. So 2.5 times the gases can be dissolved in your blood. And if you come up too fast, what happens to a dissolved gas when you release pressure? It forms bubbles. So basically the same way when you open up a soda and it makes that whoosh noise and then all the bubbles form, that's what happens to a scuba diver that comes up too quick. It's called the bends, and it's not good. So at depth, gases dissolve better. Not everything dissolves better at depth, but gases do. Temperature. Gases dissolve better at low temperatures. Some solids dissolve better at high temperatures, but gases, they dissolve better at low temperatures. So the Bering Sea, for instance, you see the Discovery Channel where they catch them big crabs, and that's always in the cold water. And then you see they also have that tuna show, Wicked Tuna, and they're always catching these big tuna in the cold water. Cold water holds nutrients and gases a little bit better than warm water. So the organisms are a little more abundant in cold, nutrient-rich water. So temperature and pressure definitely play a role in ecology, dissolved gases and dissolved nutrients. So pressure solubility, changes in pressure have little effect on solids or liquids, but gases, a great effect. And gases dissolve better at depth. Temperature, some solids increase with temperature, and that's a direct relationship. Gases decrease with a high temperature, and that's an inverse relationship. Nutrients, nitrogen-based nutrients, hold a little better in cool water. So nitrates, that's what algae use is their main nutrient. You go to Home Depot, you buy a sack of turf builder, and you spread it on your lawn. You're spreading nitrates and phosphates. And plants, that's usually the limiting factor in plant growth. We hear about all these algal blooms, and we say, oh, big sugar's polluting the water and algae's coming. It's really the fertilizer that pollutes the water, and then the algae utilizes that fertilizer and blooms. That's the process called eutrophication, or over-fertilizing. And then your water, all that algae blooms, and when it dies, it becomes anoxic, no oxygen, and then nothing can live there. So that's the danger of fertilizer pollution is eutrophication. Cooler water holds those nitrates a little bit better than warm water. This is just, I pulled this from a chemistry class just to show you how some solids, here's sodium chloride. Notice sodium chloride is pretty consistent with temperature, but you get something like potassium nitrate. It dissolves readily in warm water, but cold water, not at all. So you got warm water at the surface that gets forced down, and you have a mineral precipitate out, and that's how minerals precipitate, a change in temperature. Saturation is when your liquid's full, and then precipitation occurs once you cross that saturation point. Here's the precipitation of a salt. I'm not sure of what the salt is. It's certainly not table salt. You can see by the crystal structure, it's certainly not forming little cubes of table salt, but it is solidifying, and precipitation is the process in which crystals come into existence under the water. It's how hydrates precipitate, those methane and other hydrocarbon hydrates precipitate out. It's how the manganese nodules precipitate out at depth due to temperature and pressure changes. So salinity is the total quantity dissolved. This little, like, it's a percent sign with an extra zero. That means parts per thousand. So we're at 35 parts per thousand, or 3.5%. That's the salinity of the ocean in general. Tampa Bay, I know our salinity fluctuates from the high 20s to the low 30s, depending on the weather. As far as the Mediterranean Sea, we're up above 35 in concentration basins. So warm temperatures and high evaporation, you can be hypersaline, H-Y-P-E-R, meaning greater, hyper. Freshwater input, we call that water brackish, or hypo, H-Y-P-O, saline. So here's the Dead Sea. That's the saltiest on Earth, and this fella's floating. Why? Salty water is more dense. So things that float in water actually float higher in salt water. Fresh water or brackish water, that is where rivers, lakes, or runoff build up fresh water and dilute the water. So salinity affects properties. It changes the freezing point because it disrupts hydrogen bonding. It changes the heat capacity because it disrupts hydrogen bonding. It changes the boiling point because it disrupts the hydrogen bonding. Evaporation slows because the water is more dense. And pressure is greater when you increase the salinity. Water, the pressure of the water exerts a greater force. Ions or salts are carried to the ocean by erosion, and also volcanism supplies the dissolved nutrients. Of course, the dissolved nutrients also precipitate out or are used in biological processes. So our ocean, being it's had billions of years, has reached equilibrium. And that is called PORCHHAMME'S principle. We are in equilibrium now. That is the ratio of dissolved salts is constant because it's being added at the same rate that it's being contracted. Chlorinity is how we measure salinity. We're not having a lab, so we're not necessarily going to do this, but in oceanography labs, they measure salinity, and basically you measure the amount of chlorine in the water, chloride, and then multiply it by 1.86550, and then you get your salinity. And in an oceanography lab, you'd be given a freshwater sample, a brackish water sample, and a saltwater sample, and you'd compare and contrast the salinities. So the ocean is in chemical equilibrium because it's had these billions of years to reach equilibrium. Ions are added at the same rate they're removed. And how long something stays in the ocean is called the residence time. It can be anything from an ion to dissolved oxygen, to water itself through evaporation. The residence times is how long something stays in the ocean. The ocean also mixes. We do have, and we'll learn this with the currents, an ocean conveyor belt. And the ocean conveyor belt circulates about every 1,000 years. Dissolved gases, it varies. But temperature and pressure. great pressure, cooler temperatures, gases dissolve better. Nitrogen is the major gas in the atmosphere. It is also the most abundant dissolved gas. Nitrogen narcosis is kind of weird. I've not experienced it, but many people have. Because nitrogen is so abundant in the atmosphere, and it's also abundant dissolved, the deeper you go, the more nitrogen you have in your blood. When you reach a certain point, it starts becoming toxic and you get a little wasted, for lack of a better term. Dentists use nitrogen and in laughing gas. So basically, when you get deep enough in the ocean and the concentration of nitrogen in your blood becomes slightly toxic, it can have a similar effect as a laughing gas would. The second most abundant gas in the water and in the air is oxygen. And oxygen can be toxic at high quantities, but divers often breathe oxygen-enriched air called nitrox to allow them to stay down a little deeper to avoid that nitrogen buildup in their blood. So experienced divers are trained in nitrox diving, and it allows more bottom time. There is an oxygen minimum zone. We'll learn about that at between 200 and 1,000 meters. And, you know, right around 1,000 meters is also that sound transmission zone. We're going to be studying that when we talk about the middle layer of the ocean next week. So dissolved oxygen in the oceans, lowest, look at how low it is in this warm water, not much photosynthesis, higher in cooler water, the amount of oxygen dissolved. Carbon dioxide is also dissolved in the ocean. It also forms weak carbonic acid, which is counteracted by the carbonate cycle. We'll touch upon that in a moment, but carbon dioxide is also used for photosynthesis. Now, acids and bases, solution chemistry, water. All right, let's back it up a second. An acid is a substance with a hydrogen ion that is available for reaction. A base is a substance with a hydroxide or hydronium ion ready for reaction. Hydrogen ion is H+. The hydroxide is OH-. When you put hydrogen and hydroxide together, you come up with HOH or H2O, which of course is water. So water is neutral. Anything with a hydrogen ion is acidic. Anything with the OH- ion is basic. So water is neutral. It has the pH of 7. Anything lower than 7 is acid. The lower the number, the stronger the acid, which means the amount of H+ increases. It's not a linear scale, it's a logarithmic scale, so it really increases quickly and it's pretty strong. And the more OH- available for reaction, the more alkaline that is. So when you look at a pH scale, here's a pH scale right here, a little sample one. Notice it's not linear, it's logarithmic. So for every increase in 1, you're increasing by a factor of 10. Pure water is 7, distilled pure water. Living things, seawater, slightly basic, in the 8 range. You know, saliva, urine. Coffee is acidic. Acid rain, tomato juice. Liquid drain cleaner is very basic. Bleach is very basic. Oven cleaners. So this just gives you a sense of what pH scale is in the concentration of hydrogen ions or OH ions in the solution. We introduced that because of carbonic acid. CO2, right there, CO2, in the atmosphere or in the ocean, reacts with water, H2O, to form an acid called carbonic acid, H2CO3. So here's your hydrogen ion that breaks off. It dissociates when it's dissolved in water into a weak acid. On land, that acid falls, starts to dissolve things like limestone, structures start to crumble, builds up in lakes, and it disrupts the life cycle of organisms in those lakes, and those lakes become severely depleted. Makes soils more acidic, makes growing things tougher. In the oceans, it's generally buffered up until this point with calcium carbonate shells. We're seeing now the reduction of free calcium carbonate in the ocean because we're approaching the maximum CO2 that the oceans can handle. And once we cross that, it will disrupt the calcium cycle, which are making shells, and deplete ocean life. We're starting to see ecosystems disrupted by ocean. It's called acidification, but the ocean's not acid, it's basic, so it's becoming slightly more acidic, but it hasn't crossed into the acid range yet. And acids work the same way. They have a buffer. This carbonate reacts with hydrogen. So calcium carbonates dissolved as Ca and CO3 ions. Sodium bicarbonate. We take that in the solid form to help our tummies to neutralize stomach acid if we get acid. So this carbonate, which would normally be used with calcium to make a shell, can't be used because it's being used with the hydrogen to neutralize the acid. So our pH between 8.3 and 7.8 from top to bottom of the ocean. So, you know, we're averaging about 8. pH of the ocean's about 8 overall. So that's acid-base chemistry in a nutshell. Diffusion, here's a membrane. Little molecules can pass through that membrane from high to low concentration. Naturally, that's called diffusion. If it's permeable, things can go across it. If it's semi-permeable, only some things can go across it. If it's impervious, nothing can cross it. So water molecules are really small, and they can diffuse across most membranes pretty well. So when you use osmosis, it's the special diffusion of water. Here's a cell membrane. We're not going to study cell biology that much, but let's just take a look at the structure so we understand what's going on. Notice the size, there's water molecules, here's dissolved solids. Similar things occur when we do osmosis of water, reverse osmosis. We have a membrane, we let the water move through that smaller, the larger salts are trapped, and you soften the water and purify it through reverse osmosis. But here's a cell membrane. Cell membranes have these phospholipid tails. That's a fat tail that does not dissolve in water. So it's a phospholipid bilayer. There's your phosphate, there's your lipids, 2 layers, which prevent the passage because you have this hydrophobic water on one side. Prevents the passage of things. And then you have various protein channels, which allows things in and out. So water moves through cell membranes by osmosis, diffusion across a semi-permeable membrane. So here's cells. plant cells. And in a hypertonic, hyper means greater, tonic means salinity. In a hypertonic solution, the concentration is higher on one side than the other. So let's say you get a goldfish. Goldfish are fresh water, and you put it in salt water, your goldfish is going to die. It's going to die of dehydration because water diffuses naturally to the salt water because it has a lower concentration of water. You go to the movies, you eat popcorn, popcorn's salty, your cells dehydrate and you get thirsty because water leaves your cells to because of that salt. So salt water dehydrates living cells. Salt water is hypertonic. It has greater ions. The cell is hypotonic. It has less ions. So hypotonic has more water, less ions. So here, notice the cells are bloated and puffing up because the solution is hypotonic and the water is being forced in. So they shrink in a hypertonic solution and they overflow with water in a hypotonic solution. Point being that all organisms try to be isotonic, have the same concentration as their surroundings. So an example of that would be, say, a salmon. Salmon can live in the salt water, but when they do, they don't urinate water, they urinate more salts, they concentrate it, they offload salts from their gills to keep their isotonic. When they're in fresh water, they don't drink anymore because they have to maintain their salt, and they don't urinate salts out, and they don't offload salts from their gills. So they actively monitor their salt solution. The reason we're talking about tonicity, as it's called, hypertonic, hypotonic, and isotonic, is marine organisms have to regulate their salt to water balance. And that's an important concept in oceanography because things live in the ocean. There's salt to water balance. So if you're just looking at a cell, this explains how salinity affects the water. Notice this cell swelling up because there's more salts in the cell than the water, and the water enters the cell. This is shriveling because water's exiting the cell because there's more salt in the water around it. Just like the pictures here. These cells are bloating up because they're taking in water because of hypotonic solution. These cells are shrinking because they're losing water because of a hypertonic solution. So tonicity is a concept that we look at in oceanography simply because living things need to regulate that salt balance. So that covers our basic properties of water. Any questions regarding the lecture today?
I have a little question.
Sure.
Could you go back to slide number 52?
52 is acids and bases. Let's have a look-see. Okay.
I guess it's 53 is be rather more important. 50.
Right here, the pH scale.
Yeah, so in medicine, when people get like heartburn,
Right.
and they give them one of the best medicines is called a proton blocker.
Ah.
Now, how does that compute with your pH and your hydrochloric acid? what part of that is a proton blocker?
None of it. A proton blocker seals the cells that produce the stomach acid. It's like putting the cover on it. And then the stomach acid's not being released, so you don't get heartburn because you're blocking the acid. And then your stomach flushes out during its digestive cycle and you start fresh next time you eat. So
Well, these medicines do not, this proton blocker doesn't actually by itself create a neutralization of the
no, it doesn't.
fluids that's irritating your esophagus.
No. It stops the production of acid or
It's just that
it down to the point.
it's a sealant.
Yes.
Is that the right?
It's like a
It just-
lid. It
it
closes
seals the-
off the producing cell.
Yeah. Now, on the flip side, out of medicines like Tums that we take also to suppress acids, where does that fit in?
Now, Tums are the ones that neutralize it. Tums are what we call buffers. They react, the carbonate reacts with the hydrogen and the acid and neutralize it so it doesn't burn your cells. It just reacts out the hydrogen and it buffers it, which means it brings it to a pH of 8, your natural body pH.
So there's two different mechanisms to suppress this acid reflux, I guess.
Correct.
Thank you.
Tums treats the symptoms of high pH or low pH, I apologize. Tums treats that low pH and neutralizes it. The proton pump inhibitors stop the production of the acid.
That's great. Thanks very much.
You're very welcome. All right. If there's no other questions, then class will be dismissed. And I'll be looking tomorrow for article reviews and I'll post the quiz grades. So have a great night and I'll see y'all next week.
Hey, I had a question.
Yeah, it says Artesia.
Yep.
All right. How can I help you?
So I have a question that's not quite related to oceanography, but more about scuba diving. So scuba diving seems interesting, but something that I've heard about is sometimes when people get to really low depths, like something happens and they just like, for some reason or other, like rip their breathing thing off. Is that true? Is that something you know about or have experienced?
That is panic. I was a rescue diver for a while, so I've rescued people from panic. That's why you have two respirators. One is, if it gets knocked out of your mouth, you know where a spare one is and you can put it in yourself. But two, sometimes people get panic attacks and they'll rip their mask off or rip their respirator and try to breathe in air is a natural response when you're feeling low on oxygen. So as the rescue diver, you swim up to the person, you put your arm around them and you stick their spare respirator in their mouth. And then you make a slow ascent, cradling them. And then when you get to the surface, usually you take a 5-minute pit stop on the way up to offload gases. It's called a safety stop. But if you're in a crisis situation, you just deal with what you have and you just make sure that you ascend really slowly and get that person safe. If you're deep at a long time, you might have to do some pressure treatment in a chamber. But usually, if you follow safe guidelines, you're not down at 100 feet past your time, so you'd be okay. But those panic attacks, they happen from time to time, and I've seen it and rescued people from them in the past.
All right. I've also read a couple of reports of some people just not really panicking and just like removing their mask regardless. Like
that might be from nitrogen narcosis because they get a little bit loopy.
Oh, right. You're mentioning. Okay.
Yeah.
Would you say that there are any people who intentionally go scuba diving to get high on nitrogen?
No, I think people go buy whippets instead.
Oh, that's a good point.
Yeah, I mean, it's dangerous stuff though, because, it deprives your brain of oxygen, and brain cells, they can die. So
Yeah.
I remember when I was a high schooler, and the waitresses would fight over who got to do the whipped cream bar, that stuff. And, you come to find out a 17-year-old doesn't really know what they're doing. And then you learn, oh my God, that popping sounds, brain cells dying. Whew, you're like, oh, good. No, that's not a good thing to do. But yeah, that's it. Yeah.
All right. Well, thanks. That's all I had.
Well, great talking to you. Thank you for the question.
Thanks. Sure. Great talking to you. Have a good one.
Yep, you too. Maria, we good?